Welcome to tutorial video 6 on using my PETTaLS application, a pretty good exciter and tactile transducer loudspeaker simulator, to design loudspeakers from exciters and surfaces. This video 6 is going to be about everything that's on this simulation tab, which is not really design stuff, but just sort of like pragmatic things that you can use after the simulation has run and whatnot. Video 1 was about the panel materials. Video 2 was about panel geometry. Video 3 was about exciters. Video 4 was about weights, and video 5 was about this infinite panel velocity window. So, if you happen to be watching this video first and you're interested in using exciters that you bought from somewhere to design a flat panel loudspeaker, or you're doing research in this topic, you probably want to go back and watch the other videos first, because this one is going to reference a lot of stuff from those videos. So, I'm not going to change anything on any of these tabs just to keep it simple. I'm going to run the default simulation that comes up when you start the program, which is an acrylic panel. So acrylic is plexiglass. It's clamped at all 4 edges. It's got no box, or an infinitely large box behind it, no stands. It's about 23 centimeters wide, 35 centimeters tall, and it's got a single DAEX19CT4 exciter right in the middle of it. So I can plot the infinite panel velocity, which was also shown in the previous video, just to give me an idea roughly of what the bandwidth of this speaker is. Looks like about 100 hertz to 15 kilohertz, not terrible. So, okay, now I can run the actual simulation, which is gonna both show me what the panel movement looks like at all of the different frequencies that I'm simulating, which is this. Nothing happens at first, so I'm going to uncheck this to speed up the simulation a little bit. So I know that the first mode of this one is at like 150 hertz, so it should be around here, and then it starts splitting into these additional vibrational shapes. Cool. So, because I've shown this in the other videos, let's just skip to the end. Okay, so the stuff on this page is all about sort of simulation things. Some of this I just moved around from the previous version of the program, so I don't know. This polar plots and save data could be on the results page, but they're not. They're here, which is fine for right now. It doesn't really matter. We're getting close. We got to get to 20 kilohertz and then we're done. So I can specify a low frequency and a high frequency for the simulation. And I'm going from 20 to 2e to the 4th, which is 20,000 hertz, which is usually the bandwidth that you want to try to simulate in loudspeaker applications and human hearing applications. Within that bandwidth, there were 512 modes in the panel. Although actually I think I'd go up to 2 times the frequency, maybe? I can't remember in this version of the program. But okay, so the only results that I'm going to be referencing from the results tab are down here in the lower left corner, which is the on-axis frequency response in dB sound pressure level. And we get these 2 metrics out of the design. So we get a mean SPL of 66 roughly decibels over the entire simulated bandwidth, and a standard deviation of 15.18 dB. Again, that's over the entire simulated frequency response, which includes a lot of stuff here where there's not very much volume being produced. So, because I said here that the bandwidth of the speaker is probably going to be about, let's just say 116 to 15,680 hertz. Let's only simulate, just for the fun of it, the bandwidth in that region. I'm going to compare the results to the previous results, and we'll run this now. So in that bandwidth, there were only 400 modes, and the simulation shouldn't take as long because the frequency resolution stays the same. So there are fewer frequency points being simulated. They're not actually going to be exactly the same points anymore because it uses the same resolution but with the endpoints that you specify. So maybe that's important, maybe not. For this set of results, I don't think it's going to be very important. Okay, so we gotta get to 15,000 hertz and then we're done. So, okay, now we can see the new results overlaid on the previous results. This plot too will scale to the new frequency bandwidth. All of these other plots will scale to the new frequency bandwidth too. Oh, it looks like impedance doesn't compare. And all the rest of them do. So, okay, now in that, what I would call kind of the usable bandwidth of the speaker, we get a mean SPL of 72.33 dB and a standard deviation of 6.5 dB. Now that's on axis in a totally anechoic environment. I think that the average horizon level, I said I wasn't going to talk about this, but screw it, I am. The average horizon level is probably a better estimate of what happens when you add in all the room reflections and everything. So changing to that, we get these yellow results, which are slightly different numerically. If you just want to look at the low frequency results and run a quicker simulation, especially when you get to a lot bigger or thinner plates that have up to 1500 modes, the simulation can take a little bit longer. So you might just want to simulate 20 to 1000 hertz. Maybe that's the only region you're really interested in. So we can do that too. There's only 21 modes. So presumably this simulation should run fairly quickly. Not a lot of points to plot. And this isn't going to be all that interesting because if I wrote the code right, which I hope I did, these results should just overlay on top of the previous results, but only for a more limited bandwidth. Yeah. Looks like they're slightly different. You know, they're slightly different because of the use of only 21 modes. So they might be off by half a dB or something because there are certain modes not being included. But it runs faster. Cool. So what next? When you're done running the simulation, now I'll admit this is not super clear right now, but when you're done running the simulation, you can go up to this frequency entry box and enter in any frequency you want, and you can see what the vibrational pattern looks like. If you do that and you have a version, which I have this code written, but it's not instantiated in here because it will only be for the licensed versions of this through the university. You can look at what the radiation pattern from the surface of the speaker looks like as well, but that's not in this version. Now we have a pretty low resolution version here because I only did 21 modes, so there's not a lot to see. Let me go through and run the full simulation again while I talk about some other things. So, okay, then I want to get to this errors tab too. Now, I haven't shown any errors that can come up, but I want to let people know of what sort of entries will or will not create errors. And since I don't have the code in front of me, I'm not sure if I'm going to hit on all of them, but I'm going to try and hit on most of them, at least. So I think I capped the dimensions of the panel that you can simulate at 1 meter on each side. And that was originally to limit the number of modes being simulated. Now, I have a different way of capping the modes, so I can take that restriction off, but I'm going to leave that, again, for licensed versions of this program. Here, okay, let's look at more surface patterns. Yeah, see, it's higher resolution now. So if you want to know what the panel's doing at any one of these frequencies, you can take a look. Pretty neat. Okay, so let's look at some errors. So I'm going to set the width of the panel to 2 meters, and I'll press run. Yeah, and then this green light turns red, and it says panel dimensions should be between 1 centimeter and 1 meter. Okay, so let's set this back to 0.23, and then I'll set this one to, oops, I need a decimal point, 100 microns. That would be silly. That's like a human hair. So, I think I'm getting the same error trying to run that again. Okay, so if I change that back, now the simulation should run, and if I realized, hey, oh, I don't actually want to run this simulation, I can click stop, and it stops the simulation. I can't restart it. It'll start over again from the beginning. I could maybe someday write the code for pausing, but for right now, I haven't done that. Okay, what else? If you want to specify your own material parameters, you can, but there are material parameters that will give you an error, like a Young's modulus of 0 should give you an error. Yep, Young's modulus must be greater than 0. Okay, so let's put 3 times 10 to the 9th. Poisson's ratio of 0? I don't know. Nope, that's not an error. Okay, let's try a Poisson's ratio of -1. That shouldn't work. Yeah, okay, Poisson ratio must be between 0 and 1. Yeah, most Poisson ratios for materials are like 0.3. So can't have a negative Poisson ratio unless it's some kind of crazy alien space metamaterial thing, maybe. Although I've never heard of such a crazy, insane thing. Let's do thickness 0, an infinitely thin panel. Panel thickness should be greater than 0.1 millimeter. Oh, I didn't even let it go below 100 microns. So there you go. I have used 0.6 millimeter glass in making speakers. That's when I was in grad school. That's the thinnest panel I have ever used. So I'm sure that something might exist that would be 0.1 millimeters. That could make a speaker, but I have no idea what that thing would be. So that's as thin as we're going to go. And then I think I can go as thick as I want. 1 times 10 to the 5th meters. Let's see how that works. Yeah, 1 mode. Look at that. I think there's an error that I wrote that actually if the modes being simulated are 0, then there's an error too. And that setup didn't even give 0 mode, so I'm not even sure how you get to that. Quality factor, let's see. Quality factor must be greater than 0. Yeah, okay, so something in the equations doesn't work if the Q is 0. A Q of 1 is very, very damped. A Q of 0, I don't even know. That would be no movement, I think, at all. So Yeah, like if I set the Q to 1 and then we look at the surface. Oh, well, that's boring. Thickness 0.003. We should get back to 500. 529 modes now. What did I do? Oh, 3 times 10 to the 9th. A Q of 1 probably has like almost no vibrational shapes to it at all. This is kind of like trying to drive rubber, like foam rubber, as a speaker. Yeah, there's like not any shapes. It just doesn't, the vibrations don't spread. It's kind of boring. But, you know, theoretically, a good loudspeaker, but also theoretically a total waste of space, because at this point, why not just use a normal cone driver that's has the same piston motion but doesn't take up as much space. Yeah. Okay, cool. Density, well, now I'm running a simulation. I think, okay, so density is going to have to be greater than 0. For sure. I kind of want to show what the results from this are going to look like. I'm not going to, this is getting close to being done, so I'm not going to speed this up and put the elevator music in it like I did in the last video. We're just going to have to wait for it to finish. It's almost done. There we go. Wow, look at that. Perfectly flat response. If only such a thing actually existed. Perfectly omnidirectional, perfectly flat. My goodness. If only. Doesn't really have any modes anymore, so isn't really a modal loudspeaker anymore. Okay. You can put anything you want in for the wattage. You can put 0 in there. You can put a negative number in for the wattage, which means that the exciter is pulling instead of pushing. The only reason why that would matter is because it can put it out of phase with other exciters. So if I put 2 exciters on there with positive wattages, they will both be pushing at the same time. If I put one as negative and one as positive, they'll move like this. So I think that the exciter locations have to be between 0 and 1. So yeah, exciter is placed off the panel. Yeah. So 0.4, and then let's set this one to 2. That should give me the same error. Yeah. Nothing new there. 0.4 and 0.6, let's say. Now the error should be fixed. Yep, and the exciter has moved, believe it or not. Stop. Okay, what else? You know, I'm not sure that I put any error messages in for the cutoff frequency for the filters. So maybe don't do anything that's outside 20 hertz and 20 kilohertz for those cutoffs. Maybe I should add that in at some point. Okay, for the weights, let's hope I added error messages in for these things. Nope. So you can have, oh, hey, that's fun. You can have negative weights if you want. I have no idea what the hell that's going to do. I should add in an error message for that one. Let's see if I added in error messages for the weight locations. Nope. Okay, I gotta go back and do that. So I guess I have discovered through making this video that I need to add more error messages, because I don't know what on earth this is going to do. Just don't do that. But if you want to see some results that don't make any sense and aren't physically possible, go ahead. Okay, PETTaLS stuff is not part of this free version. All right, then what's next? The Save Data button. This will allow you to save some... I have some things here. This will allow you to save some data from the actual simulation. So I think it saves the SPL, the on-axis SPL, the velocity, and the impedance in an Excel spreadsheet or a CSV that you can use in Excel. And if you don't enter in a name here, which I think was the default for a while, it'll just, the program will make an error sound. So just make sure that you enter in a name. And then polar plots, I did this fairly quickly. This is just a standard little window that comes up with polar plots at standard polar plot frequencies, which are, oh, and it might not come up because I stopped the last simulation. So I have to run through a new simulation before I can do that. Let's make sure that I don't have a weight on there anymore. And is this still a queue of 1? Yeah, okay, that's going to be boring. So let's, to make this as interesting as humanly possible, let's give this a super high queue. Queue of 250, we'll make it glass. We'll make it 1 millimeter thick. And we'll do clamped. We'll do... I said I wasn't going to change these, and I lied. Because we'll make this a fairly interesting simulation. Let me see what this looks like. And then I'll stop it. Yeah, okay, so I'm gonna, this is as 1200 mode, so I'm gonna speed up the simulation and play some elevator music for you so we can skip right to the results. Bada boom, bada bing. Okay, that was fun. We've got our results now. Look at that gnarly thing. The very high Q gave us some kind of wacky results here. Let's see. Yeah. Very high Q leads to really sharp peaks in the frequency response. Overall, actually, like, not a terrible frequency response. With some smoothing, it probably doesn't look all that terrible. I did this, I made it a very wide speaker and with a very high Q so that hopefully the polar plots come out kind of interesting. So let's see. Yeah, not as interesting as I hoped, but they're not boring either. You can definitely see some funky radiation patterns going on here. So this, if you're used to seeing polar plots for speakers, this should look fairly familiar to you. It's at standard frequency center points, 125 hertz up to 8 kilohertz, and then radiation patterns. So if that's what you're interested in looking at, that's what's being generated here. Cool. That's all for this video. I'll see you in the next one.